Myself, Professor Vijay Devra.
I think you broke my computer thing. I think only.
Dr. Vijay Devra, are you able to hear me?
Yes. Can I start the presentation?
Yes.
Thank you. Good afternoon to everyone. Here I want to present about the applications of the green nanomaterial as a catalyst in the degradation of the organic pollutants for the sustainable development. First, I want to share about what is the nanoparticle. Nanoparticle is a very small particle at least dimension with the size range in the 1 to 100 nanometer. And nanoparticles are widely used in the synthesis of the cosmetics, medicines, and agriculture in the various industrial sectors. And depending on the number of metallic ingredients of the metallic nanoparticle is categorized as monometallic, bimetallic, trimetallic, and so on. The metal nanoparticles have the remarkable properties such as optical properties, superplasticity of the nanocrystalline materials, and hardness and strength for the nanostructure films, and quantum confinement effects, and they show the immense surface area to volume ratio. So they are widely applied as a catalyst in the various fields. The nanoparticle can be synthesized by the two approaches. First is the top-down approach, in which the bulk material convert into the metal powder and then change into the nanoparticle, where in case of the bottom-up approach, atoms change into the clusters and then form the nanoparticles. Here I am discussing about the various synthesis process approaches for the metal nanoparticle. First is the physical, second is chemical, and then biological method. But the physical and chemical method are the energy extensive route, and in the chemical method, the hazardous chemicals are used, where in case of the biological method, this is the eco-friendly protocol and cost-effective and green method. That's why we use for the study as a biological or the green synthesis for the metal nanoparticle. Here I am discuss about the green synthesis of the copper nanoparticles, in which we use the plant leaves, particularly Azadirachta indica. Commonly known as the neem. First we collect the neem leaves, then after the milling and boiling, we prepare the neem leaf extract, which are added into the particular salt. Here I am discuss about the preparation about the copper nanoparticle. Then we add the copper salt. As the passes of the time, the color of the suspension are changes from green to dark brown, which confirm the formation of the copper nanoparticles. Then the synthesized copper nanoparticle were characterized by the different instrumental technique. As you can show the different color of the suspension of the nanoparticle, we confirm the as the passes of the time, the color of the solution are changes. Finally, we get the dark brown color, which indicates the formation of the copper nanoparticle. That is confirmed by the UV visible spectra. UV visible spectra explain about the different wavelength when we get the absorbance at the different interval of time. As the time passes, the wavelength of the nanoparticle increases. Finally, we get the 570 nanometer, which confirm the formation of the copper nanoparticle. And the synthesized nanoparticle are also characterized by the transmission electron microscope study and the surface area electron diffraction study. And the time analysis, results of the time analysis explain about the synthesized nanoparticle are in the cubical shape. with the average size of particle is 49 nanometer. And the X-ray surface area electron diffraction pattern indicates the synthesized nanoparticle are highly crystalline. Now, as we know that in the leaf extract of the Arctica indica, the many phytochemicals are present, such as riboflavin, terpenoids, polyphenols. These phytochemicals are applied as act as a reducing as well as the capping agent for the synthesized nanoparticles, which is confirmed by the FTIR spectroscopy. As we can see, the wavelength number 3400 and 2902, which confirm the OH molecule stretching. It means the water molecules are present on around the synthesized nanoparticles, and many CH 1614 and 13282. These stretching confirm the CH and CN stretching of the phytochemicals present in the neem leaves, which are act as a reducing as well as the capping agent. So synthesized nanoparticles are highly stable in the 4 degrees centigrade for the 1 month. Now, the synthesized nanoparticles are applied as a catalyst for the degradation of the various organic pollutants. As we know, the textile industry effluent contain large amount of the dye chemicals, which may cause severe water pollutions. So, due to the water pollutions, plant species, aquatic animals, human beings, environment are affected due to the dye effluents. So, we need to degrade them into harmless product. Here I am discuss the role of the synthesized copper nanoparticle in the dye degradation. There are the many processes available for the removal of dye by biological, physical, and chemical process. These methods are often very costly and not eco-friendly due to their low efficiency and large amount of slug generation. And here I'm discussing about the advanced oxidation process, which have the draw attention due to their high efficiency and selectivity towards pollutants, and in which the generated sulfate radicals are useful for the degradation of the organic pollutants. Here you can see the UV visible absorption spectra of the oxidative degradation of orange G is a organic pollutant, and as the UV spectra suggests, the reaction mixture of orange G initially consists 3 main peaks at the 254, 329, and 476 nanometer. And the band at the 245 and 329 arises due to the pi-pi transition, which are attached to the aromatic ring of the N double bond N group in the orange G molecule, whereas 476 nanometer band could be assigned to the N-pi transition of the N double bond N group. As reaction proceeded, it was observed that the characteristic absorption peak almost disappeared within the 16 minutes in the presence of the copper nanoparticle, which indicate that the chromosphere and conjugated system were being destroyed into the harmless products. This is the proposed oxidative degradation route for the orange G in the copper nanoparticle peroxomonosulfate system. The proposed degradation route revealed that the generated sulfate radicals initially attack on the aromatic ring, leading to the loss of characteristic fragments such as 77, 30, and 64 groups and converted into the harmless product. Now, I am discuss here about the comparative kinetic study of the copper nanoparticle catalyzed degradation of the methyl orange by the peroxomonosulfate and peroxodisulfate. And here I am discuss about the catalytic activity of copper nanoparticle in the both system, copper nanoparticle peroxomonosulfate and copper nanoparticle peroxodisulfate system for the degradation of the methyl orange. Here I also discuss about the various effects of the reactant concentration on the degradation rate, and the results indicate the pseudo first order kinetics and activation parameters were also determined, and LCMS results indicate the intermediate arising from the methyl orange by the copper nanoparticle system. The UV at 465 lambda maximum degrade within the 30 minutes, which confirm the methyl orange degraded into the copper nanoparticle peroxomonosulfate system, which is also confirmed by the LCMS results. Here we show that as the time passes at a 0 minute, this is the indicate the methyl orange structure. After the 10 minute, the degraded into the another intermediate, and finally converted into the less harmful products such as nitrite and sulfite. And this is the proposed oxidative degradation of the methyl orange in the copper nanoparticle peroxomonosulfate system. And this is clearly indicate that the methyl orange degraded in the presence of the copper nanoparticle into the harmless products. Now I'm discuss about the various kinetic parameters such as effect of dye dependence, as we show in the both system, peroxomonosulfate and peroxodisulfate system. The rate of degradation of methyl orange initially increases up to at a particular concentration of the dye, that is the 5 × -5. After that, the rate of degradation of methyl orange is decreases as we increase the concentration of the dye at the fixed concentration of the other reactant concentrations and condition. And the peroxosulfate dependence, first is the peroxomonosulfate initially increases as we increase the peroxomonosulfate concentration, the rate of reaction is also increases. After that, the rate constant is almost constant, because at higher concentration that the active sites of the peroxomonosulfate is the constant. So this is the limiting factor, and so rate of degradation of the methyl orange is also constant. But in case of the peroxodisulfate, as we increase the concentration up to 5 × -5, the rate of degradation of methyl orange is also increases. But after beyond the higher concentration of the 5 × -4, the rate of methyl orange is decreases, which is due to the side reactions of the sulfate radicals are involved into the side reactions. And the more consumed, then the more consumed of the peroxodisulfate, hence the percentage of the peroxodisulfate decreases with the increasing the concentration of the peroxodisulfate at the fixed concentration of the other reactant and conditions. Now, the effect of the initial pH. When copper nanoparticles was dispersed in water, then the surface become cationic in nature, which would more coverage of the hydroxyl group from the water. So uncharged surface hydroxyl group of copper nanoparticle were the main active sites for the generate sulfate radical. Thus, as pH increases, the degradation rate is also increased and reaches the maximum at the pH 6.5. After that, catalytic surface become anionic and higher electronic force to repel the sulfate anion. So less sulfate radicals could reach the catalyst surface. The rate of degradation decrease correspondingly at the higher pH. And this is the when we see the effect of copper nanoparticle on the degradation of methyl orange. As we increase the concentration of the copper nanoparticles, the rate of reaction is degradation of methyl orange is increases, because the more active sites are available as the copper nanoparticles concentration increases. And here we see the effect of temperature, that if the temperature increases, the rate of generation of oxidizing species such as sulfate radicals and higher valent copper species also increase. So the rate of degradation of methyl orange was accelerated by the rise in the temperature. And here we calculate also the activation energy in the both system by the plotting the graph between the log K versus 1/T. The activation energy is 21.64 in the case of the peroxodisulfate, and in the case of peroxomonosulfate, minus 13.19 kilojoule per mole. And the scavenger effect is also studied. As we know, in the advanced oxidation process, sulfate and OH both radicals are active. So we determine the effect of sulfate radicals. We use the ethyl alcohol and tertiary butyl alcohol to see the effect of scavenger. And as we see in both cases, in the presence of ethyl alcohol, the reaction is totally constant. It means the scavenger effect of the OH, which confirm the formation of the sulfate radical in the reaction. As an active species, this is the mechanism of the degradation of the methyl orange in the presence of the sulfate radical and the copper nanoparticles. As in the case of sulfate radicals, copper nanoparticles convert into the copper ions and sulfate radicals, and sulfate radicals then degrade the copper dye into the form the harmless product, and copper nanoparticle are again regenerated. And now the time of the conclusion, the reactivity discrepancy of peroxodisulfate and peroxomonosulfate followed the order of copper in the presence of peroxomonosulfate is greater than the in the presence of the peroxodisulfate in degradation of methyl orange under the similar condition. And the elucidation of degradation pathway is of special interest considering environmental priorities. And these nanoparticles showed a significantly longer lifespan with the sustainable reactivity, making them the potential application in the dye degradation. These are the many more applications in the presence of metal nanoparticles. This is my study. And the conclusion of the total study is the use of neem leaf extract for the preparation of the copper nanoparticle is inexpensive, and this is the eco-friendly route, and the plant extract based synthesis can provide the nanoparticle of controlled size and morphology. And the present phytochemical in the plant extract are act as a reducing as well as the stabilizing agents, so we can prepare the nanoparticle without any protecting gas. And the smaller size of the particle of the nanoparticle and higher concentration of peroxomonosulfate, peroxodisulfate, catalyst, and higher temperature promote the degradation of the orangey and methyl orange dye in presence of the peroxomonosulfate as well in the peroxodisulfate system. And the LCMS analysis result indicate the degradation of azo dye into the harmless product. Thank you. Any question? Thank you so much for the giving the opportunity of the Catalysis Forum. I am very, very thankful to Catalysis Forum to give me this opportunity. Thank you so much.
Thanks a lot for your presentation, Professor. Any questions from the group?
Any question?
Doctor, I think we have a question from TV Rajeshwari.
Yes, please.
Dr. Rajeshwari, do you have any questions?
Yeah, thank you for giving me opportunity. My question is, have you checked the size of the copper particles effect on dye degradation?
निकल गई? हाँ निकल गई. हाँ एक मिनट बात करते हैं. ठीक निकल गए? 2 मिनट है ना, निकल गए क्या? Hello, pardon. Please repeat again, please.
Yes, ma'am. My question is, what is the effect of the size of copper nanoparticles on dye degradation? Have you checked that one?
Yes. From the TEM analysis, which give the about the size of the nanoparticle, which is the 47 nanometer.
That is you have characterized the prepared nanoparticle size. But my question is, size
In the
is
dye
best
degradation.
for
Yes.
Yeah.
No, madam. This is the because this is the quasi-homogeneous. It is not possible to determine the size of the nanoparticle during the after the degradation of the dye molecule. But it's a good suggestion. I will try in the next research.
Hello. Thanks a lot, Professor, for your presentation. Could you please permit us whether to upload your presentation in our YouTube channel? Hello. Hello, Dr. Vijay Devra. Are you there? Okay, so let's move on to the next presentation. Professor